The atmosphere in motion. In this chapter, we're going to be discussing air pressure, wind, highs and lows, as well as the circulation of the atmosphere and also precipitation. Now, what is air pressure? Simply put, it's the pressure that's exerted by the weight of air above a given point. On the diagram below, you have X that's on a flat surface. We see the column of air, which is applying pressure to point X. Now, at the very top of the column would represent the top of the atmosphere. Average air pressure at sea level is about 1 kilogram per square centimeter, and that's used as a standard measurement. Measuring air pressure. Now, most commonly referred millibar or inches of mercury, that's the unit that they use to measure atmospheric pressure. Now, the barometer was invented by Evangelista Torricelli in 1643. It simply allowed atmospheric pressure to be applied onto a mercury dish, and mercury would rise as atmospheric pressure increased. As it decreased, the mercury levels would drop. This still holds the standard for measuring atmospheric pressure. Aneroid barometer. Now, this was invented by French scientist Lucien Vitti in 1843. It was smaller, more portable, and had no liquids compared to the original barometer. Now, this worked in a way with a vacuum chamber at the very bottom. It would compress and expand as air pressure increased and decreased. This would in turn change around levers, which would move a spindle with a pointer representing inches of mercury. Now, on a standard at-home use aneroid barometer, you can see stormy, rain, change, fair, or very dry, trying to represent what weather would be in these levels of atmospheric pressure. Now, although atmospheric pressure doesn't directly correlate with weather, at most times it can represent what weather could be if you record it properly. The barograph was created to allow us to record continuous changes in pressure over time with an aneroid barometer. You would set them up and meteorologists would be able to record either on a daily level or on a weekly level of the different changes in the atmospheric pressure for a certain location. Now, what causes wind? Wind is basically the result of horizontal differences in air pressure. So simply put, air flows from areas of higher pressure to areas of lower pressure, which gives us wind. Now, solar radiation is the ultimate energy source for most wind. Here we have a weather map with isobars. Now, atmospheric pressure measurements are shown on surface weather maps using isobars, which are basically the lines connecting places of equal air pressure. Typically, the isobars are not straight, and they usually have a curved motion. Here we have an example of the pressure gradient force. Basically, we have the isobars represented here with high and low pressures, and the spacing between the isobars indicates the amount of pressure change occurring over a given distance. Now, closely spaced isobars indicate a steep pressure gradient and strong winds, while widely spaced isobars are weak pressure gradient and light winds. The Coriolis effect. This was named after French engineer Gustave Gaspard Coriolis. It's a force of deflection due to Earth's rotation, which affects all free-moving objects, fluids, and even wind. Deflection is to the right in the northern hemisphere and to the left in the southern hemisphere. You could see this in our tropical storms. While they move clockwise in the northern hemisphere, they will move counterclockwise in the southern hemisphere. You can also see this like the US Navy did during World War II. During long-range practices, they noticed that they would miss their seemingly stationary targets by as much as hundreds of yards. Due to the long range, the Coriolis effect would change the course of the ballistics. Now, over short distances, the Coriolis effect is relatively small. However, long ranges, you can notice the difference. Here we have an example of geostrophic winds. Now, as soon as air begins to move from its starting point, the Coriolis effect acts as a right angle to the motion. The faster the wind speed, the greater the deflection. Eventually, the Coriolis effect will balance the pressure gradient force, and the wind will blow parallel to the isobars. Upper air winds generally take this path, and that's what you get, a geostrophic wind. Now, the lack of friction of Earth's surface allows geostrophic winds to travel at higher speeds than surface winds. Speeds can reach up to 50 to 100 miles per hour. Jet streams are considered the most prominent features of upper level flow. They are approximately 2,000 feet up in the air, and they were first actually encountered during World War II by high-flying bombers. They travel west to east at a rate of 120 to 240 kilometers per hour. One such stream actually is over the polar front, which is the zone separating the cool polar air from warm subtropical air. Cyclonic and anticyclonic winds. Cyclones are centers of low pressure, while anticyclones are the opposite, so they are centers of high pressure. Now in the example here, we see an example for the northern hemisphere. Arrows can show wind blowing inward and counterclockwise around a low, and outward and clockwise around a high. Weather generalizations. Meteorologists determine that with a low or cyclone, they have converging surface winds and rising air, which result in cloudy conditions. And highs or anticyclones typically have diverging surface winds and descending air, which leads to clear skies and fair weather. Now, this is great for short-range weather predictions. However, it is still difficult to map out for big tropical storms as they are constantly changing. Circulation of the atmosphere. Now, the underlying cause of wind is unequal heating of Earth's surface. In tropical regions, more solar radiation is received than is radiated back to space, while in polar regions, the opposite is true. Less solar energy is received than is lost. So attempting to balance these differences, the atmosphere acts as a giant heat transfer system, moving warm air poleward and cool air equatorward. Here we have an example of circulation on a non-rotating Earth. Basically, the heated air at the equator would rise until it reached the tropopause, which acts like a lid and deflects the air poleward. Eventually, this upper-level airflow would reach the poles, sink, spread out in all directions at the surface, and move back toward the equator, where it will begin the cycle again. Here is an example of the idealized global circulation. It's simply broken down into 4 pressure zones. We have the subtropical and polar highs, which are areas of dry, subsiding air that flows outward at the surface, producing the prevailing winds. The low pressure zones of the equatorial and subpolar regions are associated with inward and upward airflow, accompanied by clouds and precipitation. The influence of continents on the atmosphere. Now, large land masses such as Asia become cold in the winter and develop a seasonal high-pressure system from which the surface flow is directed off the land. And in the summer, the opposite occurs. Land masses are heated and develop a low-pressure cell, which permits air to flow onto the land. These seasonal changes in wind direction are known as the monsoons. During the warm months, areas such as India experience a flow of warm, water-laden air from the Indian Ocean, which produces the rainy summer monsoons. The winter monsoon is dominated by dry, continental air. A similar situation exists, but to a lesser extent, over North America. The westerlies. The circulation in the mid-latitudes, the zone of the westerlies, is complex and doesn't fit the convection system proposed for the tropics. Between 30 degrees and 60 degrees latitude, the general west to east flow is interrupted by the migration of cyclones and anticyclones. In the northern hemisphere, these cells move from west to east around the globe, creating an anticyclonic flow or a cyclonic flow in their area of influence. Local winds are small-scale winds produced by a locally generated pressure gradient. There are 3 types: land and sea breezes, mountain and valley breezes, and Chinook and Santa Ana winds. Here we have land and sea breezes. To the left, you have a sea breeze, which develops because cooler air over water moves toward the warmer land. To the right, we have a land breeze, which develops when the land cools more rapidly than the sea. Mountain and valley breezes. To the left, we have an example of a valley breeze. The air along the slopes of the mountain is heated more intensely than the air at the same elevation over the valley floor. Now that warmer air is less dense, so it glides up along the slope and generates a valley breeze. This happens during the day. At night, rapid radiation cooling along the mountain slopes produce a layer of cooler air next to the ground. Cool air is denser than warmer air, so it drains downslope into the valley. This is considered a mountain breeze. Warm, dry winds sometimes move down the east slopes of the Rockies, where they are called Chinooks. Now to the right, we have a Chinook-like wind that occurs in Southern California. These are the Santa Ana winds. The Santa Ana winds are dry, which increase the threat of fire in an already dry area. Wildfires fanned by Santa Ana winds raged in Southern California in October of 2003. The fires scorched more than 740,000 acres and destroyed more than 3,000 homes. Measuring wind. There are two basic wind measurements, direction and speed. The instrument most commonly used to determine wind direction is the wind vane. Wind speed is commonly measured using a cup anemometer. When the wind consistently blows more often from one direction than any other, it's called a prevailing wind. Below you can see a wind vane as well as the cup anemometer that is used to determine the direction and the speed of wind. Global distribution of precipitation. Regions influenced by high pressure with its associated subsidence and diverging winds typically experience relatively dry conditions throughout the year. Regions under the influence of low pressure and its converging winds and ascending air receive an ample amount of precipitation throughout the year. Thank you for watching the presentation on the atmosphere in motion. I hope you guys learned something about our atmosphere.